So here is a back of envelope calculation first. So suppose we look at two possibilities of multicasting a file of a fixed size. Okay. The fixed size is f bits, and we look at the first possibility, which is going from the server to all the clients. Okay. So these are the clients 1, 2, 3, 4. Each client has a certain download speed, D1, D2, D3, D4. And then the server needs to upload this, and it has a total of U sub s as the upload speed. Okay. So now we have to look at the time that it takes to finish multicasting this file of fixed size f bits. First, we have to make sure that even the slowest downloaders among the clients can finish receiving. So let's denote the slowest downloaders download speed by d sub min, the minimum one, and it has to finish downloading a file size of f. So that's the amount of time it takes. And second, the server need to multicast this, therefore need to do it n times. In this case, n equals 4, but in general, n is the number of clients. So I got to look at the time it takes to send out n times f bits using the speed of U sub s, the upload speed of the server. So U sub s for server. And these two numbers, one of them may be smaller than the other. So that would be the bottleneck. And therefore, we take the minimum of these two numbers. And that would be the answer to the question, how long does it take for client-server architecture to finish sending this, multicasting this file? Now, in contrast, suppose we do it in P2P fashion. Then the server only need to send this out in the ideal case, only to one of these peers. So that only take f divided by U sub s time. Of course, this file needs to be downloaded by even the slowest downloader. So f divided by d min term still remains there. And now we have to make sure that altogether, eventually, nf number of bits needs to be sent around one way or another. And the ideal case is that everybody's upload speed are used, including the server's upload speed, U sub s, and the summation of all the upload speed from all the peers indexed by I, from 1 up to n, because there are n such peers. Okay. If you can indeed achieve this bound, this is the most ideal situation where everybody's upload speed can be utilized, then you can say, well, one of these three numbers will be the smallest of the three, and that will become the bottleneck. Whether it's the server sending one piece of the one copy of the file out, or the slowest downloader, or the fact that some of these upload speed might be slow. But since I'm using all the peers as servers, I can leverage all of them. Assuming this can be achieved, then we have this formula. The min of these three numbers, okay, whichever turns out to be the bottleneck, is the answer to the question, how long does it take now? Now, if I compare this formula with the formula on the last slide, which is this one, they look kind of alike, but there's a crucial difference. Over here, as n becomes big, okay, n goes to infinity, for example, soon enough, this term will dominate that term. So we're going to have to I guess I had a verbal typo, and this should be the max. Of course, we're talking about the time it takes. So whichever is the longer time. So this should be the max, and this should be the max. Okay, I'm not talking about the speed, but the time it takes. All right. So as the n becomes very large, this will dominate that term in picking which one is the larger number, which one is the longer delay component. Then this term will dominate. And how does this term scale with the size of the network? That's the scalability question. Well, linearly in n. If there are more clients, you spend more time, and that is intuitively trivial to see. Okay, as you keep adding more clients, eventually this server will be loaded. In contrast, in this formula, we see three terms. These two terms do not scale with n, so as n becomes big, they will be dominated. It will be this term that matters. And as n becomes big, what would happen to this term? Well, the numerator will go up linearly in n, but assuming the upload capacities are somewhat reasonably distributed numbers, then as n becomes big, the denominator also grows like n. And therefore, that cancels each other out, and we have a self-scaling property. Again, intuitively, that's crystal clear because the more receivers you add, more destinations you add in a multicast, you also add more sources. Okay? So that's the back of envelope. But this assumes the ideal situation where you can indeed utilize everyone's upload capacity. That doesn't have to be the case. In fact, that generally speaking is not the case. For example, in graph A, we have a particular tree. This is the server, okay, the blue rectangle. And then we got 4 pairs A, B, C, D. And this is a tree because all the chunks will traverse like this. Okay, this is a tree. The parent node go down to this, go down to this, go down to this, has another child node down there. Okay, so you can also draw it like this. That's the tree. Okay? There is only one way to go from the root node to any of the leaf nodes, and there's no cycle. Whereas in fact, just look at this graph, you see that, hey, since node A is the parent of nodes B and D, so the upload capacity of node A is utilized. Since node B has a child, its upload capacity will also be utilized. But what about nodes C and D? They are the leaf nodes, and therefore they are only on the receiving end, and their upload capacities are entirely wasted. So C, D upload capacity are wasted. And clearly, we wouldn't be able to achieve this bound. What if we use another tree? In this case, the root will go to C first, and C go to D, and then D go to A and B. This is another tree. In this case, AB's upload capacities are not used. Their upload capacities are wasted. That's not good either. So whichever tree you pick, you're going to waste somebody's upload capacity. But wait a minute, what if I use both? In fact, what if I use many trees? Each tree is a multicast tree, and there will be some waste of upload capacity. But if I use all of them, maybe that will be helpful. For example, I can use another one where the root go down to A first, okay, and then A goes to C, C goes to D and B, right? This is the server. These are the 4 peers. Okay, that will be yet another tree. I can build many of these trees. I show just 3 trees here. Now, of course, you have to make sure that the upload capacity across all the trees for each pair is not exceeding its total upload capability. For example, node A is used here and here. So you better make sure that the rate you assign on this tree, okay, say 10 megabit per second, and on this tree, say 20 megabit per second, A has to be able to support both trees. So you have to make sure A has at least 30 megabit per second kind of upload capacity. Okay, so you have to carefully manage where you place each pair in each tree. But you see the problem. The problem is embedding multiple trees to support the same multicast session in a general graph, possibly with constraints on, say, the number of children nodes you can have, degree bounds. And this is a very difficult combinatorial optimization problem. Okay, it is not a continuous problem like what we've seen before, like in last lecture in TCP congestion control. This is a graph theoretic optimization problem. In the advanced material, we will look at approximation methods, again using primal and dual problem to solve this in approximated fashion. But we can look at the exact answer through interesting development in the coming 5 to 10 minutes for a special ideal case. But the intuition should be clear that those pairs with a large upload capacity should be placed closer to the root of the tree and support more children, and possibly show up in more of these trees too. Okay, that is the intuition. And here is the example. The example I want to look at is that, well, I have a source, okay, the root or the server, okay, indexed by denoted by S. So I have this server sitting there with a certain upload capacity. Okay, that's the original sender, and I have n peers. They each have a certain upload capacity UI, and this one got U sub S. So you cannot violate UI and U sub S constraint. Now the question is, how can you construct multiple trees so that you can achieve this bound? Okay, so let's first write down the bound, and we'll come back to this picture in a minute. So here's the bound that you would like to show that you can achieve, right? You want to say that the time that it takes to finish multicasting this is the max of 3 terms. Let's say ignore the download speed. Okay, let's say the download speed is fast enough even for the slowest downloader. Let's just look at the bottleneck from upload capability. So you're looking at the max of these 2 numbers. Oops, running out of space. Okay, that's the denominator here. So you want to show this is true, okay, where t is the total download time. And this is equivalent to saying that the maximum rate that you can achieve across all these multicast trees is the min of the reciprocal of these. Okay, US over F and US plus this summation UI over NF. Okay, the smaller of these 2 numbers, because the largest rate is simply proportional to 1 over the time it takes. Since F appears on both, let's just assume it is 1 unit. Okay, whether it's 1 megabyte or 1 gigabyte doesn't matter. Okay, that means we want to show Rmax equals the mean of 2 terms, US and US plus summation UI over N. Okay, fine. This captures the essence of the self-scaling property. So we basically say that if the US is actually bigger than US plus sum of UI over N, which is, roughly speaking, the average upload capacity counting both server and all the peers. If that's the case, you've got a pretty powerful server. That's very good. That's one case. Okay, then the answer is that Rmax should equal to the smaller of the 2 term, that is this term. The other scenario is that you got a pretty obsolete server. Okay, its upload capacity is very small for whatever reason. So US is actually smaller than the average of the server and all peers upload capacity. In that case, Rmax should be the smallest of the 2. That is, it should be equal to this. So let's look at these 2 cases. So case 1, let's say your server is not a very powerful one. So US is less than US plus summation UI over N. Okay, this is the condition here. And now, what kind of trees shall we construct? We are basically going to construct the following family of trees. There will be n trees, 1 for each of these n cases. Each of these cases, you have a 2-hop tree. Okay, the depth is 2. It goes to one of the n peers, and then that pair will become the parent node for all the other n-1 pairs. And you do the same thing, except you swap the position of this parent pair. Okay, now it becomes pair number 2, and then it goes down to the other n-1, 1, 3, up to n pairs. And you repeat this. Now you've got n trees, and I say that I'm going to do multicast simultaneously using all these n trees. Don't worry about this tree yet. We'll come to that in the second case. And I need to show you that I can assign the right rate, a multicast rate, for tree 1, rate on tree 2, up to rate on tree n, so that the summation of these rates will achieve my target, what I want to prove, which is it should be equal to the smallest of these 2 terms, that is U sub s. That's what I need to prove. Okay. And also I need to prove that it's also feasible allocation of rates on these trees, because I need to show it doesn't violate the US or the UIs. All right, so let's first show feasibility and then show achievability there. So the feasibility is easy to see. Okay, here's my solution. The solution says that I will let the rate on each tree I, there are n such trees, to be simply a fraction of the upload capacity of the server. What fraction? Well, the more capable you are, the more larger share you're going to shoulder. It will be proportional to the UI relative to the normalization, okay, of all the upload capacities, j from 1 up to n. Okay, this is your peer number I upload capacity, and then you look at the sum of all the upload capacities. Okay, so if the sum is 10 and you are 2, it's like you are 20% of the capabilities of the peers, and therefore you're going to take 20% of the job. You can take 20% of the upload capacity for the tree where you are the parent pair, serving the other n-1 peers. And I conjecture this answer is A, feasible, and B, optimal. Let's look at feasible part first. Is it feasible for the server? Well, sure, of course, by construction, it is trivially true. Add up all the rates on these trees, n of them, which equals the summation of ui over summation of uj us. Well, these two cancel each other, you get us. Very good. Not only is feasible, you can smell something good because it's fully utilizing all the upload capacities. Okay, this one's upload using all the server's upload capacity. That's a good sign. What about the upload capacity for each pair? Well, each pair need to say that I am the parent node in one tree and one tree only. Okay, and that tree has a rate Ri, and I need to support n-1 children. What is this? Well, this is simply by the definition of my expression for the rate on each tree I equals this. So I need to say, is this expression indeed less than or equal to ui? That's the question mark. Okay, I need this to be smaller than or equal to ui. Is that true or not? Well, that's equivalent to ask, we can cancel ui on both sides, whether n-1 times us divided by sum of uj's is less than or equal to 1. That's equivalent to ask if n-1 times us is less than or equal to summation of uj. Still a question mark. I don't know if that's true or not. That's equivalent to asking whether us is less than or equal to n times us, less than or equal to us plus summation uj. And that's equivalent to asking if us is less than or equal to us plus sum of uj over n. Is that true? Okay, I'm carrying this question mark over. Well, let's look at the condition here. The very premise behind the case 1 is that us is smaller than the us plus some ui over n. I'm just changing this dummy index variable from I to j here, otherwise it's an identical expression. And therefore, this is indeed true by the very first assumption that defines what's case 1. Case 1 is your server capacity, upload capacity is not big enough. All right, so this is true, therefore this is true, therefore this is true, and therefore it is indeed feasible. Very good. Now, is it also achieving what we want to show? Okay, what do we want to show again? We want to show that the total rate under this allocation of per tree rate equals the mean of these two numbers, and in this case that means equals u sub s. So that's what we need to show. Well, what is the total rate achieved? We claim to be the maximum rate. It is the sum of all the rates that each pair gets. Well, first of all, pair I is getting a certain rate directly from the source, from the server, remember. If you are, say, peer 1, in this tree where you support the n-1 peers, you are getting a rate of R1 direct from the server. And then for n-1 other trees, you are getting the rate that's given to you. You now become a leaf node from the other n-1 peers. So on your own tree, you're getting Ri, and on the other trees, you're getting Rj for j not equal to I. But hold on a second, this is the same as summation of Ri over all the i's, which is the same as summation write-down expression for Ri ui over sum of uj times us. Us doesn't even depend on I and j. These two terms cancel each other. That equals us. Done. We have proved what we wanted to show. Okay, Rmax in this case 1 is indeed achieving the formula U sub s. Very good. So in the case where your server isn't powerful enough, we found a way. Okay, simply by assigning in proportional terms the upload capacity to different multicast trees rates. We have shown it is feasible and achieving the answer. So what about the other case, second to last case? Now in this case, your server capacity is pretty powerful. Okay, US is bigger than US plus the summation of ui over I divided by n. Okay. So in this case, we want to show that Rmax equals the small of the two terms, that is equals to this term. Can we do that? Well, turns out in this case we're going to need not just n trees that are 2 hops trees, but also another tree, one more tree. That's a 1 hop tree. Intuitively, what happens is that since your server is so powerful, even after finishing talking to n trees and let each of them talk to the other n- trees, I still have some leftovers. The leftover capacity for this server upload capacity is going to be utilized. You can't just let it go waste. If you do that, you won't be able to achieve this nice result. So you have to do the following. Okay, you can just give the leftover, whatever that is, directly in a 1 hop tree. It's actually just a star topology. It's a client server topology to all the other n nodes. Okay, all the peers, and this we label as tree number n+1. So all we need to do now is to assign the right rate for each of these n trees and assign the rate for the n+1 tree, and then show it's feasible and achieving the right answer. So I'm going to claim that now I can assign the rate on each tree, the first n trees, to be simply the corresponding pair, that's the parent pair in that tree. Okay, that pair's upload capacity divided by n-1. Now this makes sense because then I know immediately that it satisfies all the upload capacities, because it is the not a leaf node only in one tree, and in that tree it is the parent node serving n-1 children. So n-1 times Ri is nothing but ui. So you are clearly fully utilizing each individual user's upload capacity. Very good. And what about the n+1 tree's rate? Well, that's actually easy to calculate. You just look at the server's upload capacity, okay, minus the summation of all the upload capacity. Okay, each divided by n-1. Okay, so that is Ri, the summation of Ri. This is the Ri term across all the trees. All right, this is the leftover capacity. And as we just talked about, you just spread it evenly among these n pairs. So the rate is going to be this. And this immediately implies that the upload capacity of the server is fully utilized and not violated, because what is the server capacities, what is the server's total upload loading? Well, you need to upload to all these entries, and that is summation of ui over n minus 1 summing over I. Okay. Then you need to support talking directly to n pairs with the rate of this n plus 1th tree. Okay. And what is that? Well, if you just look at the rate there, you multiply n over there is nothing but us minus the sum, and therefore you add the sum, that gives you nothing but u sub s. So again, you fully utilize and do not violate the upload capacity of the server, just like what you did with each of the n clients, n peers. All right. So by our design, we have demonstrated that it is feasible. This way of constructing trees and assigning the rates on them is indeed feasible. It doesn't violate upload capacity. The only thing left is to show that it is achieving our target result. All right, let's look at what is the rate that any pair I receives. Any pair I's receive first the rate directly from the server in the ith tree, where is the parent pair. And then there are n minus 1 trees where is receiving this from the other pairs. Okay. So if you are pair 1, you got some rate direct from the server in this tree, and then for the other n minus 1 trees, you got the rate as a leaf node from the other n minus 1 pairs. Very good. And then there's the n plus 1th tree, the last tree, where the server shares the leftover upload capacities. That is the rate on that tree. Now you can plug in the definition of these Ri, Rj's and that star topology tree, and cancellation of the terms lead you to nothing but us plus ui summation over I divided by n. Exactly what we wanted to achieve. Okay, R max should be the smallest of the two. In case 2, this is the smaller of the two, and that's exactly what you get. In other words, now we have proved, combining both cases 1 and 2, that R max is indeed the mean of us and us plus summation ui over n. Now that implies, therefore, the time it takes to download is the max of 1 over us and n over the sum of us and all the ui's. That's exactly what we wanted to show. So in this ideal case with no topology constraints and so on, we have actually shown the back of an envelope calculation. This calculation is indeed achievable. So in advanced material, we look at a more general case and a much tougher cases for approximation results. But let's summarize at this point. We have seen the power of building overlay networks, whether Skype or BitTorrent, immensely popular internet services. And this P2P law quantifies the positive network effect in application layer multicast context. And we've just demonstrated through the back of an calculation example that you do not need to have a degree that grows as a linear function of number of nodes. A smart pairing can do a magic. And ideas such as tit for tat also solves free rider problems and enable the BitTorrent to scale up. And that is the scaling up property for P2P. In next lecture, we'll look at the scaling up property of a different kind of content distribution system, the cloud.